Hello friends, welcome to my YouTube channel. Hope you are doing well. I have created this channel only for CFD beginners, those are interested to excel their career in the field of CFD. I have added some basic example of CFD simulation for to familiar with the CFD workflow. At the end of the problem, you will know how to add geometry, how to set up model, how to set up boundary condition, how to set pre-processing, and how to see result through post-processing. So let's go to start with simple example using ANSYS Fluent. First we will define the geometry. So go to the geometry. Now import the geometry. I have created the geometry in Creo. Open the geometry in it will take time at first. In the design modular, we will define the inlet, outlet, wall. Yeah, once it is open, click on the generate. Uh, if you see the model, intentionally I have made a half portion of the mixing chamber due to the symmetricity, due to the symmetric feature. Yeah, first we will go to the problem statement. So this is the fluid flow and heat transfer in a mixing elbow. It is a three-dimensional turbulent fluid flow. We will predict the flow field and temperature field in the area of mixing region in order to properly design the junction. What we will learn? We will learn how to set material property and boundary condition for a turbulent force convection problem. Also we will see this how to set up a surface monitor, then solver method to increase the convergence speed. This is our mixing chamber, and if you can see we have the larger inlet. This is, we can say, the inlet 1, and we have one smaller inlet, we can say inlet 2. In a larger inlet we have the boundary conditions, that is the velocity 0.4 meter per second, temperature 20 degrees Celsius, and intensity is 5%. For the smaller inlet we have the 1.2 meter per second, temperature is 40 degrees Celsius, and I is 5%. So from the lower inlet the hot water will flow, and from the larger cold water will flow. Also we have given the density, viscosity, conductivity, and specific heat. In the problem they have given the Reynolds number. Based on that we can find out it is a laminar flow or turbulent flow. And Reynolds number is greater than 3500, we call it as a turbulent flow. And before start to in design modular, first we will set up the unit as per the boundary condition. So I will switch to design modular. Now you can see here we have one part or one body, that is the fluid. We also called as the domain, fluid domain. So first step is to set the inlet or to define the inlet boundary. So here you can select there is a selection filters. You can see this is for point, this is for edge, then this is face, and this is the entire body. So we need to select face. So just click, right click and say names selection. Here you can specify inlet 1 and generate. Now you can see in the tree outline we have the inlet 1 here. If you select, it will show on the model. Just rotate and select the smaller one, then go for the new inlet 2. Okay, good. Then we'll define the outlet. So select this and name selections outlet. Then we'll select this face and we'll say this is the symmetry. And now we'll select the entire body as a wall. Name selection, sorry, this yes, now this is the wall. Okay, yeah, here you can also go to the view and unselect the frozen body, so you can see the clear image or model. So here we have defined our the inlet, outlet and symmetry and walls. Once it is done, save it. I will save on my local drive. New 020 flow through my mixing chamber. Flow through mixing chamber. So the next part is we have to do meshing, and for that I will attach mesh. You can use this mesh or like this, or you can directly call the fluent. So in that also we have the with meshing, in this also we have the mesh. So it is on up to you. So basically my practice is I use meshing and I attach the setup. So here just double click. So our meshing environment will open. You can see here it's pop up here starting meshing. It will take time. in tripod, you can just say to Z or click Z direction, so your model is parallel to your screen. Now you can see this is our geometry. We have meshing here, and already we have defined this our name selection, inlet and outlet and symmetry. So in the mesh, so you can see this is the detail of mesh. Here you have to keep as it is body color. Instead of mechanical, we have to select CFD. Yeah, solver preference is fluent. Then we'll go to the sizing. In sizing, we'll select the proximity and curvature. So if we have the curvature, a small curvature in the mixing chamber, so that will be covered in the meshing. Relevance center should be fine. If you want a chorus mesh, then you can set as a chorus. Transition should be slow. Then we'll set the, yeah, here you can also see the quality. This we will see later on. Once it is done, just right click on the mesh and generate mesh. Yeah, now you can see in a smaller inlet we have the fine mesh here. Yeah, then we will see the quality of the mesh. For that you have to go for the mesh matrix, and you can see generally we see the aspect ratio, then orthogonal properties. Yeah, you can see it is nearly 1, so it is a good mesh, and we have to avoid these smaller things. It is above the 0.5. Below 0.5 we have to uh, redefine the mesh in that area. Also you can see the skewness. Yeah, so it has to close to 0. So yeah, then we'll save it. And we'll close the meshing part. Yeah, then we'll attach fluent setup, and you can see here now it's showing yellow. It means we have to update this before to set the pre-processing. Here update. Yeah, now you can see it is a green mark. Now go to the setup, right click, or you can double click directly. Here we will take a double precision. Our processor is in a serial, and then our model is not a 2D, so default it took 3D. Yes, Now first step is the unit. We have to change the unit as per our boundary conditions. So we'll see what was given in the boundary conditions. Yeah, so density is given, that is all, density is already in the same unit. uh, might be we have to change the conductivity or specific heat. We will see this in later stage, but before that we will change the temperature. Temperature unit in Kelvin, so we will set as degree Celsius. Okay, so our solver is a pressure base, it is not a density base, and it is a steady state simulations, so we have not selected transient, and later on we will select the model, as we have mentioned that in the problem description that RE Reynolds number is given. So based on the Reynolds, so our problem is a turbulent, so we'll use the turbulent model for the same. And before that we have to on the energy equation. In the viscous laminar you have to change the K epsilon. Then first we will go with the standard, and in later example we will see the rest of the options. Here you can see select the standard. In near wall treatment, if you are given the layer, if you set the layer, then you can go for the standard wall functions. We'll say okay. Yeah, so we have defined our model, that is the K epsilon. Next stage is we have to set the material. So default air is in the list. We need a water, so we'll create a material, go to the Fluent database and just click here W water liquid H2, say copy, close. So you can see we have the water name and chemical formula is given. Fluid type is not a solid, it is a fluid, and here we have to change the property as per given in the description problem statement. So we'll see what is the value. So density is given 1000, it is almost 1000, so but we will set what we have, what is given 1000. Then specific heat in joule per kg Kelvin, so it is given 4216. Then the thermal conductivity is in watt per meter Kelvin, so it is a 0.6, so 0.677. And viscosity is given in kg per meter second in SI unit, so it is the same in Pascal second, so we will set that. Ten raised to 4 only, sorry. Okay, now change it and close. So now you can see in the list we have the fluid and air. So we have defined the material. We'll go to the next cell zone. Here we have the fluid as a domain. So here you have to change to the water liquid, and boundary conditions, then we have to define boundary condition. Now you can see already we have defined this inlet 1, inlet 2, then outlet, symmetry. So all these options will come here. So you have to set first inlet 1, edit. In inlet 1 we will use the magnitude and normal to boundary conditions. Here we have the 0.4 meter per second is given and turbulent intensity is 5. In the thermal we have the 20 degree Celsius temperature. For the inlet 2 it is the 1.2 meter per second given and temperature is 40 degrees Celsius. Then the symmetry is a symmetry edit, and for the outlet is 0, and we can keep we'll keep a temperature as it is, that is the atmospheric, and we'll say OK. Then for wall it should be a wall zone, so it is a stationary wall, it is not a moving wall, so we'll select the stationary as a default. Or you can also set the temperature for that if you know the temperature of the body. So we have defined the boundary condition as well. So now in a reference value, here you can see automatically it computes from the 1 point velocity. It is given here. So in the drop down list we'll select inlet 1. So we have defined so it will start from the inlet 1. So you can see here all the properties here in the method. As we have seen in our presentation that we will also see the Solver method to increase the convergence speed. So the basic we will see the first simple, and then we will go for the coupled one. So in coupled it will your convergence speed will be increased. So here you can see the least square cell method. Pressure should be a second order, momentum is second order, turbulent kinetic energy is first order. Keep as it is as default, and also as mentioned we'll then go for the initializations. Initialization we will use the hybrid. Say, now you can see it showing hybrid initialization is done. Now you can go for the run, but before that I think we need to set some okay, that we will see later on. We'll go for the run. Here the number of iterations I will go with 150 iterations, and we'll see. Yeah, before that, yeah, we'll see the monitors, our residual plot. For the XYZ we'll keep 3 10 raised to minus 3, and for energy it will be a 10 raised to minus 6. Okay, now we'll see OK, and then we'll go to the run. we have mentioned 150 iterations, and we'll say calculate. uh, how we can know the our problem is converged or not? So for that we have to check some parameters. We'll see that once the convergence is done. We'll see. Now you can see here this reading is going down down, and after 10 raised to 3 it will be steady. So it means that our convergence is correct. And the second method is that we have to see the reports. In the reports, that imbalance should not more than 2%. Yeah, now you can see calculation is done. Okay, yes, now you can see. Yeah, yeah, as I mentioned that report, we have to check the flux for mass flow rate and inlet 1, inlet 2, and outlet, and we have to say compute. Now you can see the imbalance is less than 2%. Once it is done, then we'll go for the post processing. But before that, okay, go to the graphics. In the contour, we will see the velocity contour. Velocity. So here you can select field, these first four options, and then go for the velocity and velocity magnitude. We'll see on the symmetry plane directly. It should be coloring should be smooth. Now display. Go to the viewing and just opt the lighting so image will be clear. Now you can see here. Yes, now here we have the inlet velocity 1.4. So you can see this red area, it is 1.39, and here at inlet 1 we have given 0.4. Next we'll see new, and we'll see the pressure distribution. Pressure distributions, again choose first 4, then go for pressure, static pressure, and again smooth and symmetry. Yeah, now you can see here, you can save it here. Now you can see the pressures. So here is pressure drop little bit. Also in same manner we can see the temperature distributions. static temperature at symmetry plane. Yes, so as we have defined 40 degree at a small inlet and 20 degree at inlet 1, so we have the 19 at inlet and 1 and 40 at inlet 2. Yes, here you can also see the vectors or path particles. We will see one. We will create a new, then vector, velocity vector, we can say velocity vector 1, then velocity color velocity magnitude here in the symmetry and display. Now you can see, if you want to see clearly, then increase the scale 1.5, maybe more, 3, yeah, 6. Yes, now you can see the vector, velocity vector. In same fashion you can check the temperature or pressure vector. Yeah, then also we'll define the surface monitor as we have mentioned in our problem description, that then we'll go to the setting up domain, then surface, create here ISO surface, and you can choose here mesh. In Z coordinate we have to check and just say Z outlet and choose outlet and compute. Now here value will come automatically, then create, go to the plot, in plot XY plot, new, select XY plot, and here you can go for the temperature, static temperature, and select Z coordinate outlet and say plot. Now you can see this is the average plot. Also you can go for the surface monitor and create another surface monitor for the pressure and compute. New, then choose pressure static pressures from the same plot. Yeah, now you can see in the plot we have two, or you can directly select or say plot. Yeah, so in this problem we have seen how to import the geometry, how to define the boundary conditions, then we have seen the meshing. After that we have seen the post processing. In that we have seen we have defined the boundary condition, we have defined the material, we have set the model as per our problem descriptions, and in the post processing we have seen the temperature, pressure, contour. Yeah, we will see more example in the mixing flow chamber in my next video. Thank you very much.